Hello and welcome back to my infrared YouTube channel. Today's topic is weather and clouds and what do they have to do with infrared, which is partly interesting as an application, but it's also partly interesting if you want to do infrared astronomy. First, I will talk a little bit about atmosphere and absorption. Then give a very short intro into weather forecasting, and in the end show a couple of examples of cloud imaging in visible and infrared. Here top right there is a formula and an explanation how the air gets thinner with height. And there's a simplified formula that more or less shows you that the pressure goes down with an inverse of an exponential function. And this function here depends only on the height, but of course it's more complicated because it also depends on the temperature, which makes it a bit more demanding. But more or less you can see on the graph here that the pressure goes down a lot very quickly and then only very slowly over the 100 kilometers of altitude. What happens to the temperature is more interesting, because first in the troposphere where the weather is, temperature goes down from, if you rise up from sea level to 10 or 11 kilometers, and then it's going to be stable until 20 kilometers or so, and then in the stratosphere temperature goes up. And why is that? It's because the stratosphere absorbs some ultraviolet, and then the stratopause, there's again no temperature change, and in the mesosphere the temperature goes down with height, which is normally what you would expect in a gas. And then again there's the mesopause, and in the thermosphere temperature goes up again. And this has to do with absorption of X-rays actually coming from the sun. Now here I have the energy balance of the atmosphere and the ground. When the sun sends in light, mainly visual light, a lot of it would reach the surface of the Earth, and a little bit gets absorbed and goes into the atmosphere and heats it up. The atmosphere itself has a temperature, so it will radiate out some long-wave infrared, and some of it will also radiate to the ground. And the ground also has a temperature and will radiate some light, especially infrared light, of which a lot is absorbed in the atmosphere and only a little bit goes through out in space. Without an atmosphere, the Earth would be quite cold on average, which is roughly minus 18 degrees, whereas the atmosphere is like a warm jacket and keeps us warm, some 32 degrees on top of what it would be without. So the Earth has an average temperature of 14 to 15 degrees, which is really a nice temperature to live in, on average. Here I'm going to show you some clouds in the low, middle and high compartment of the troposphere. Most of them are strictly in one of these heights, but there's one exception, which is the cumulonimbus that goes through from the ground to reaching the tropopause where the stratosphere begins. And most of the clouds that just come in and don't change a lot, but as you know, in summer, when you have a summer thunderstorm, a cumulus can get larger and larger and rise up and make a cumulonimbus. Whereas for these nimbus stratus clouds, they normally come in and rain and leave again and still rain. High clouds, they are rather interesting for astronomers because they deteriorate your pictures, and they're consisting of ice crystals mainly. And if the sun or the moon shines through, you can see a large halo. Whereas in the middle part, if you have alto cumulus or the respective stratus for alto cumulus, you have a small halo. You can see the sun or even the moon dimly through it, but just as a brighter part of a cloud. And here I listed the gases that the atmosphere consists of and also the absorption spectra of these gases. For example, the Earth's atmosphere has a lot of nitrogen and quite a bit of oxygen, which make up 99% more or less of the atmosphere, which is only if you calculate the atmosphere as dry atmosphere, because water content can be up to 4%, even without clouds. And roughly 1% is argon and a little bit of helium and neon. But there are also molecules like methane and oxygen as a molecule, and ozone and CO2 and water, and also nitrogen oxide. And as you can see here, each of these gases has its absorption spectrum. For example, oxygen absorbs a lot of ultraviolet light, and especially ozone does that. Whereas, for example, CO2 only starts to absorb in the shortwave infrared up to long-wave infrared range. And water and CO2 almost absorb almost the whole of the infrared together. There are some windows that are coming through though, which is a good thing for us observers. But you can see here that water is more or less the largest part of it, which means being in a dry place, you see lots more infrared. Now I'll give a very short crash course in weather forecasting. These are the wind and high and low pressure zones that basically every planet has. The Earth, like Jupiter, for example. Around the equator you have a low pressure zone, and then you have a zone with northeast trade winds, and then there's a subtropical high, and then there are winds, west winds, relatively widely between 30 and 60 degrees north and south, and then there are northeast winds, and then you have a polar high. So on the pole there's only very little snow, coming down. Whereas around the equator it's almost raining almost every day. And these zones move a little up and down with the seasons. So in north summer, everything will come north, and in north winter or south summer, everything will go south. So you can be in different of these zones across the year, but it doesn't change very quickly, it changes with months. And this tells us where the main winds come and also where the cyclones come. For example, here on the map there's this cyclone, or there's a very nice one shown here, also on the cloud image and here on the weather map. And these lines show the fronts between warmer and colder air, and along these fronts you often see lots of rain. Because if the cold air cools down the warmer air will rain out. And this more or less shows what happens if a cyclone crosses you. It's coming and then you run into the warm front, and then there's a little bit of nice weather in the middle, not in the middle of the cyclone, but a bit south of the middle of the cyclone, and then there's cold front with a thunderstorm, and after the thunderstorm you have roughly one day of nice weather until the next cyclone of a family will come. And you can even depict the type of clouds that you're gonna see. First there is some cirrus, so you could guess that the cyclone is coming, and then cirrostratus, altostratus, and finally nimbostratus. And when you see the nimbostratus, it's raining already. And there's a warm sector in between here, and then cumulonimbus that give rain but not very long, quite windy. And then in the backside weather, it's high pressure more or less, relatively high pressure. But this, what I told you, takes account only the air and the water in the air that is coming to you and is leaving from you. It can also happen that it condenses in your place, especially if you live on a mountain or on the wind side of the mountain. Now I'm going to show you a couple of cloud images. Some people are observing clouds scientifically, like the ones shown here. Here in Switzerland, in Davos, there is one of these cameras that show long wave infrared of the whole sky with a mirror. Why should you take long wave infrared and not visible light? You could take visible light during the day, but long wave infrared you can also measure during the night. And here I took some pictures of some clouds in the visual, in the near infrared, and in the long wave infrared. It's a bit easier to see structure in the visual than in the long wave infrared, whereas the near is somewhere in between. And here is a picture from the visual range as it could be seen in an early spring day with lots of cumulus clouds. And there are also some high clouds here that are probably cirrus or cirrostratus. And thank you for the attention.